In this video, we are going to learn how to evaluate double integrals in polar coordinates. This is going to make integrating over circular regions much simpler. Starting off, if function f of xy is continuous on a polar rectangle, R, given by these bounds, where R is bound between a and b, such that a and b are both greater than or equal to 0, and theta is bound between alpha and beta, where there is an extra requirement on alpha and beta, and that is the difference, beta minus alpha, has to be between 0 and 2 pi. This requirement is so that we don't overlap any of the region more than once. Right? So the difference between the two angles has to be between 0 and 2 pi so that we ensure we only cover the region one time. Then the double integral over the region R of the function f of xy dA is equal to, and we're going to pause here. Before we convert this double integral to polar, let's look a little bit more closely at the region that we're integrating over. So let's draw out a polar region. So we'll draw two lines that indicate the angles, and then we're going to draw two portions of a circle. So there's our region R. And based on the definition above, the inner radius is A, so R equals A. The outer radius is B. And then as far as the angles go, this would be alpha, the smaller of the angles, and this would be beta. And just like with any other integration problem, as we're integrating over this region, really what we're doing is dividing this up into smaller and smaller rectangles. Right? So we can visualize that by drawing a few lines inside of the region, breaking it into rectangles. Now these are what we call polar rectangles. And let's highlight one of these. So we'll pull one of these out. So there is our polar rectangle. And we need to do that because we have to figure out how to find the area of that polar rectangle for this dA component of the integral. Okay, so we can kind of extend the sides of that polar rectangle back to the pole or the origin. And now we can label this diagram to figure some pieces out. So in this diagram, here is R. Right? So R defines the inner radius. And then the change in the radius from the inner to the outer, that's going to be delta R. The change in the angle, that's going to be delta theta. So then the side length here of the polar rectangle requires a little bit of side work. If we remember arc length formula was S equals theta R. So the length of this side of the rectangle is going to be theta, which is delta theta here, times R. So R delta theta. So now we have the sides of this polar rectangle defined. Now, it is important to point out that the side is curved, but we are working under the assumption that this rectangle is so small that we can basically ignore the fact that this side is curved and treat this just like a normal rectangle. So that means the area of this rectangle can be defined as length times width, or at least approximated with that. Okay, so we can say the change in the area, so we'll go delta A. Let's fix that delta. So we can say delta A, the change in the area is going to be approximately equal to R delta theta times delta R. Okay, so the change in one of these small area subrectangles is equivalent to the area of this polar rectangle, which we can work under the assumption that it's a rectangle and use length times width. Now more formally, and more importantly for us setting up the double integral, this is going to turn into dA equals R, and then delta R will be dr, and delta theta will be d theta. I switched the order just to match the order that we typically write this in. So we have r dr d theta. So this is our first important piece of development, that dA, when converted to polar, becomes r dr d theta. And that arose from this side being slightly curved and us using the arc length formula to find the side of that polar rectangle. So now going back into our double integral and converting it to polar, we're going to have the double integral. We need to convert the function to polar. So wherever there's an x, that becomes our cosine theta. Wherever there's a y, that becomes our sine theta. If you recall those conversions, dA becomes r dr d theta. And the bounds on r, in the definition above, that goes from a to b, and the bounds on theta go from alpha to beta. And now we have converted this double integral into polar. For me, the most important piece is this r dr d theta element that is in place of the dA. Without this factor of r, many of the integrals become more challenging than they do if we include the r. Conversions, right? And we'll talk throughout the video about the conversions into polar, but this is what a polar double integral is going to look like. Now, in this particular example, we set it so that the region was defined by two circles, two different radii. Now, what happens when this expands and this is not a perfect circle that is bounding the polar region? So, if we consider a general polar region, now we're bounding r by functions of theta. So g1 theta and g sub 2 of theta. Those are functions of theta that are going to bound our region. So what that is going to look like, we still have our same angles. And now, instead of drawing the portion of a circle, maybe we have some sort of curve that's defined by theta. So here, this inner radius is g sub 1 of theta, and the outer radius is g sub 2 of theta. Angles still defined the same way. We have alpha as the smaller angle and beta as the larger angle. This is now the region R that we're integrating over. Same idea, we break it up into smaller subrectangles. We take the area of those polar rectangles, accumulate them over the process of double integration. We're integrating over this region. How that affects the double integral, we have the double integral then, still converting our function. So wherever there's an x, there's a cosine theta, a y, r sine theta. And then dA becomes r dr d theta. Now r is going from functions of theta, so g sub 1 of theta to g sub 2 of theta, and theta is going from alpha to beta. Right, so here the difference, the change, is the fact that the inner bounds of integration will be or could be functions in terms of theta. One thing I want to point out that relates to single variable calculus, if we assume this function was equal to 1, as we've discussed with our double integrals, then this would represent area. And we'll talk about that separately, but just for now, if you think back to integrating single variable integrals in terms of polar, you always started the integral in the form of 1/2 r squared d theta. Well, if we integrate r with respect to r, we would get 1/2 r squared. So that's another way to show why the single variable polar integrals start with 1/2 r squared d theta. Most of the time in single variable calculus, we take a geometric argument to develop that. Here we can take a double integral method to understand why it would become 1/2 r squared. There's another justification for this factor of r that we will cover at the end of this unit when we talk about change of variables, but we won't get too far ahead of ourselves. Last thing I want to include on this page as a helpful reference are the conversions that we may use when we're working in polar. So two that we already talked about, x is r cosine theta, y equals r sine theta. We also have x squared plus y squared equals r squared. And also tangent of theta equals y over x. All of these will be helpful as we work to convert into polar coordinates to set up our double integrals. Now let's work through a few practice examples. So evaluate the following double integral by converting to polar. So the double integral over the region R of x squared plus y squared dA, where R is the region bounded by x squared plus y squared equals 9 in the first quadrant. So let's start by visualizing the region. So we can draw the first quadrant, draw the portion of the circle of radius 3. So this is the region that we're integrating over. So it is a circular region, so polar is going to make sense here. So that's the region that we're covering. So we can convert the double integral. So x squared plus y squared is r squared. dA is times r dr d theta. All right, so just to highlight again, that's our dA component. And now we need to define the bounds on r and the bounds on theta. So if we look at our region, r is going to go from 0 to 3 as we work outwards from the pole or the origin. And theta is going to start at 0 and work its way around to pi over 2. So 0 to pi over 2. All right, so if we mark up our diagram, just to understand, basically going out this way is our r, and sweeping along that way is our theta bounds. So one thing to point out here as we work through this example, our bounds are constants and our function is only in terms of r. So this is going to be separable. And that is one of the nice things about converting to polar, is from time to time we will create separable double integrals. So in this case, we can say the integral from 0 to pi over 2 of 1 d theta times the integral from 0 to 3 of r cubed dr. Won't always happen, and it's a little bit tricky because that's definitely not a rectangle, but really what we're thinking about are polar rectangles, so that works, that connection works here and creates a separable double integral. Okay, so we can integrate simultaneously. That's the advantage here. So we get theta evaluated from 0 to pi over 2, and then 1/4 r to the 4th evaluated from 0 to 3. So that's going to give us pi over 2 minus 0, so pi over 2, and then times, plug in 3, 81 over 4 minus 0, so just 81 over 4, so 81 pi over 8. So there is the answer we get after we converted this double integral into polar coordinates. Next example, same directions, double integral over the region R of x squared plus 3y dA, where R is now the region between the circles x squared plus y squared equals 4 and x squared plus y squared equals 16. So now we're going to have a ring that we're integrating over. So we can draw it just to get a visual of where we are integrating. So we'll draw the circle of radius 2 and the circle of radius 4, centered at the origin. So the region that we're integrating is this ring in between those two circles. Okay, so convert our double integral. So double integral of r cosine theta squared plus 3 times r sine theta dA times r dr d theta. I'm going to put an extra set of parentheses here because it is important we distribute the r to both terms in our double integral. The bounds on r go from 2 to 4 and theta go from 0 to 2 pi. We work our way all the way around the circle. Now, in this instance, our bounds are constants, but our function cannot be expressed as a product of r's and thetas, so we do not have a separable double integral. That means we have to integrate one variable at a time, which we've done plenty of, but just wanted to point out. So 0 to 2 pi, 2 to 4, so r squared times r, so we have r cubed cosine squared theta plus 3r squared sine theta dr d theta. So integrate with respect to r, we get the integral from 0 to 2 pi of 1/4 fourth r to the fourth cosine squared theta plus r cubed sine theta, evaluated from 2 to 4 d theta. So we have the integral from 0 to 2 pi of 4 to the fourth over 4, so that's really just 4 cubed, so that will be 64 cos squared theta plus 4 cubed, which is 64 sine theta, minus 2 to the fourth, 16 over 4, so minus 4 cosine squared theta, minus 2 cubed, 8 sine theta d theta. So we can combine our like terms here. So that's going to be integral from 0 to 2 pi of 60 cosine squared theta plus 56 sine theta d theta. Now we do have a cosquared term here. So in order to integrate that, we have to substitute in the cosine double angle formula. And if we manipulated that out, that would give us 1/2 plus cosine of 2 theta over 2. So we're going to make that substitution. And we'll do that by distributing the 60 out too. So integral from 0 to 2 pi of 30 plus 30 cosine of 2 theta plus 56 sine theta d theta. Okay, now that we've done our substitution work, we can integrate with respect to theta. Focusing on this middle term, we would underline 2 theta. If we were doing a traditional u substitution, that would be your u. Then du would be 2. So I can break this up into 15 times 2. I'll circle the 2, which would be the du in a traditional u substitution. And now we can integrate term by term. So that's going to be equal to 30 theta plus 15, integral of cosine is sine, so 15 sine 2 theta. And then integral of sine is negative cosine, so minus 56 cosine theta. Evaluate that from 0 to 2 pi. So that's going to be 60 pi. And then sine of 4 pi is 0. Cosine of 2 pi is 1, so minus 56. And then plug in 0, so minus 0. Sine of 0 is 0. And then cosine of 0 is 1, so minus a negative will be plus 56. So that gives us 60 pi as our solution. So here's an example of a polar double integral we were not able to separate, and we had to go through the iterative process of integrating one variable at a time. Now, we're starting with a double integral that's already been set up in terms of x's and y's, and we're going to recognize that converting to polar is going to be easier here. Now, that recognition happens for a few reasons. So in this particular integral, we're taking the double integral of e to the x squared plus y squared dx dy. X goes from 0 to the square root of 2 minus y squared. Y goes from negative square root of 2 to square root of 2. For me, there are two things that stand out that would indicate converting to polar would make a lot of sense. First, this upper bound is x equals the square root of 2 minus y squared, which is the graph of a semicircle. In this case, it's the graph of the right side of the circle of radius rad 2. The other part in the function, we do have an x squared plus y squared, which will convert nicely to polar as well. Let's focus on taking the region out and drawing it. So as I mentioned, this is the right half of the semicircle of radius rad 2, and then y goes from negative rad 2 to rad 2. Right? So if we were drawing like a type 2 rather, we'd go from left to right, so from 0 to the square root, so we'd work our way all the way from the bottom to the top of that region. But I'm now going to mark this region going out from the pole or the origin, because now we want to think in terms of polar. Just to show you a little bit of algebraic manipulation here to help, right? If you didn't see that this was the semicircle right away, we could have squared both sides, so x squared equals 2 minus y squared. X squared plus y squared equals 2. So we would have at least gotten to the place of realizing this is the circle of radius rad 2. And then because it started as x equals the positive square root, that would have indicated that we were dealing with the right side semicircle. Okay, so now we can go through the process of converting. So convert our function, so e to the r squared, and then this is our dA, and in polar, dA is r dr d theta. R goes from 0 to the square root of 2, and now theta here, we do want to cover this region in a continuous manner, so we do want to start down here and work our way around the region in the counterclockwise direction. So that means we want to start at negative pi over 2 and work our way around to positive pi over 2. So we're going to go from negative pi over 2 to pi over 2. And that's an important fact right there, that we sometimes have to use negative angles so that we are covering the region in a continuous manner. We don't want to overlap it. We don't want extra. We really just want to define the region that we are dealing with in a continuous manner. So these bounds on theta allow us to do that. Now here we do have another separable. All right, so I'll note that. So separable double integral. So we can go integral from negative pi over 2 to pi over 2 of 1 d theta times the integral from 0 to the square root of 2 of r e to the r squared dr. So integrate with respect to theta is theta. Evaluate that from negative pi over 2 to pi over 2. And then underline r squared. If it were a traditional u substitution, that's your u. The derivative is 2r, so that would be your du, but adjust it by dividing by 2. So this integral is 1/2 e to the r squared, evaluated from 0 to the square root of 2. So that gives us pi over 2 minus a negative, so plus pi over 2. And then square root of 2 squared is 2, so 1/2 e squared minus e to the 0 is 1 minus 1/2. So in the first set of parentheses, pi over 2 plus pi over 2 is pi, and then times this. So I'm going to factor a 1/2 out just to make the answer look a little cleaner. So this is pi over 2 e squared minus 1. So we have the pi times the 1/2 we factored out, pi over 2, e squared minus 1. We could have left it distributed with the pi or the 1/2. All those answers are equivalent. This answer just, for me, looks simple. Last example, double integral of 6y dy dx, where y goes from 0 to the square root of 2x minus x squared, and then x goes from 0 to 1. So if we notice, there's a slight difference in that upper bound with the x there that's going to change the region that we're integrating over. So let's draw out our axes. First thing we want to do is visualize the region that we're integrating. So y equals x. Easy enough. Now what's a little harder is figuring out what this region is going to be. So y equals the square root of 2x minus x squared. In order to visualize it, let's do a little bit of algebraic work. So y equals the square root of 2x minus x squared. So we can square both sides. So y squared equals 2x minus x squared. Move everything over. So x squared minus, not plus, minus 2x plus y squared equals 0. If we complete the square, so half of negative 2 is negative 1, square it would be plus 1 on both sides. Factor would give us x minus 1 squared plus y squared equals 1. So this is a circle of radius 1 centered at 1, 0. So 1, 0, radius of 1. So that circle is going to look like that. And the region, if y goes from x to the square root of 2x minus x squared, as a type 1 region, we draw our vertical lines in this little region up here. Now we're going to define this in terms of polar, so I'm going to start at the pole or the origin and cover that region working outwards. Okay, so let's start the process of converting this to polar. So 6y is 6r sine theta. and then dy dx is the dA, so in polar that becomes r dr d theta. And now we need to figure out the bounds on r and the bounds on theta. So r is bound by this circle that's centered at 1, 0 and has a radius of 1. So first thing we need to do is convert this equation to polar. So I'm going to take this line as opposed to the most simplified version. I think it's easier to simplify in the form of x squared minus 2x plus y squared equals 0. So x squared plus y squared is r squared, and then minus 2r cosine theta equals 0. And let's just redo that because that theta did not look great. Cosine of theta equals 0. So we can factor out an r, and then we have r minus 2 cosine theta equals 0. So either r equals 0, which is definitely not the circle that we drew, or r equals 2 cos theta. And that is the circle that we drew. So the equation of this circle in polar is r equals 2 cosine theta. R equals 2 cosine theta. So r, as we drew those lines out from the pole, or the origin, we start at 0 until we hit that circle. So our inner bounds of integration are going to go from 0 to 2 cosine theta. And now we need our bounds on theta, which first thing is the y equals x. What angle does y equals x define? So y equals x, if we convert that to polar, so y equals x is really r sine theta equals r cosine theta. If we divide both sides by r cos theta, that gives us tan theta equals 1. And tangent theta equals 1 at 2 points, but the point that we care about would be theta equals pi over 4. The other would be 3 pi over 4, but that's not relevant here. So this first angle is theta equals pi over 4. And then we need to figure out the second angle, which is when that circle hits the origin or the pole. So we need to figure out where 2 cosine theta. Notice there's a lot of work on the right side of this page, and we haven't really done any integration yet. So when does 2 cosine theta equal 0? Cosine theta equals 0 when theta equals pi over 2. So our bounds on theta are from pi over 4 to pi over 2. Now, one thing I do want to note about r equals 2 cos theta, so those circles that go through the origin but are not centered there, their period is not 2 pi. Okay, so here the period of the graph is pi. So that means if we wanted to integrate over this whole circular region, so imagine y equals x wasn't there, and the region was just this circle, r equals 2 cosine theta. Our theta bounds would be from 0 to pi, not 0 to 2 pi. 0 to 2 pi, we wind up doubling this region, which would double our answer. We're going to explore that in other problems, but I want to make note of it here before it comes up later on. So now we can integrate. This is not separable because we have a function of theta in our bounds. So this was the second slide of the video. So we have the integral from pi over 4 to pi over 2 of integral 0 to 2 cos theta 6r squared sine theta dr d theta. So integrating one at a time, we have the integral from pi over 4 to pi over 2 of 2r cubed sine theta from 0 to 2 cosine theta d theta, which equals the integral from pi over 4 to pi over 2 of 8, so 16 cosine cubed theta sine theta d theta. Cosine theta would be our u in a traditional u sub. Negative sine theta would be the du, but then I need to put a negative in front of the 16 to make that adjustment. So integrating u to the third would be u to the fourth over 4. So we can take that from the negative 16. So negative 4 cosine to the 4th theta. Evaluate that from pi over 4 to pi over 2. So we have cosine pi over 2 is 0, minus, so plus 4, times cosine pi over 4 square root of 2 over 2 to the 4th. So that's 4 times 4 over 16, which is equal to 1. So the value of this double integral is 1. So we hit a lot of different cases, which is great. We saw an example where our bound was in terms of theta. We saw examples that were separable, but the more examples that you practice with, the more cases and the more ideas that you're going to come across. Practice with this, make sense of it. Polar is definitely going to make things easier overall as we progress into our triple integrals as well. See you in the next video.